how you feeling?
All right. Good morning. Eventually, it arrives Friday, right? That's a long week. Okay, so let's do overall. I'm picking up. Alex. Derek. Oh. Danish. Joshua. Kaushik. Five. Sonia. Luigi. All right, so today is a due date for the second programming assignment. And let's go through the instructions. So basically we have 4 rules. The first one is how you should name the file. If you work with a team, then both last names should be in the file name. And then if you work alone, then just put your own last name. And then you should put full names, no matter you work individually or in a group on inside the Word document. And everybody, even you work with a team member, you should submit a copy to D2L. Then some students feel that a single file is more convenient. That's fine, but you should still need to have three separate parts for each of the questions. That's fine. Okay, so we already have some submissions. Now let's check whether they follow the rules or not, right? So Kendall, you did a good job. Then Sean also is good, all these are good. Then Seth. So I assume that you are still working with Alex, right? Mm-hmm. Then, the name, your submission didn't follow the rules, right? So you should put your last name as well as Alex's last name. So, so is Alex's submission. So you guys need to resubmit. Yeah, so pay attention. The deadline is midnight today. And if you don't like the deadline on Friday, then I can change it to the weekdays if you like. Not for this assignment, for the future assignment. Okay, so do you have any questions? Okay, so now let's review what we started in the last class. So still, let's talk about the motivation for the new cost function and the new updating rules for the logistic regression. So why we want to make changes? So what's wrong with linear regression? So the main problem is that linear regression is not bounded, right? So, and for binary classification, we want the value, the output of the hypothesis function bounded between 0 and 1. So that is the motivation. And since linear function is not bounded, we want to add an additional function to help the linear function bounded. So that's why we add additional sigma or sigmoid function. So this is sigmoid function. That's 1 over 1 plus e to negative W transpose times x. So here sigma is called sigmoid function or logistic function. That's why the binary classification is called a logistic regression. So basically, a neuron now is doing two things. The first, it calculates the linear function. Then the output will be fed to the sigmoid function so that the output is bounded. Then, what does the output mean theoretically? So the output is between 0 and 1. Then what does that mean?
Probability.
The probability, right? That's the probability that the output being positive. Then we also studied the decision boundary. So this is the hypothesis, this is a curve for the output of hypothesis function. So if the output is greater than or equal to 0.5, then we classify that case to be positive. Otherwise, we classify it as negative. So in order to make the output of the sigmoid function greater than or equal to 0.5, then what's the requirement for the linear function? Linear function should be greater than or equal to 0. Then the output is positive. Otherwise, output is negative. So that's why we discussed this example for the decision boundary. So pay attention to x1 and x2. Pay attention, x1 and x2 are two features. And in order to classify them, we should make the hypothesis function greater than or equal to 0. So that means, we derive a line that is this one that can separate the positive case from the negative case. So we also studied the new cost function, that is a y, negative y times log h of x minus 1 minus y log of 1 minus h of x. So then we also studied the gradient descent. So in terms of the updating rule, the weight updating rule, it is same, right? It's same as the linear regression. It is just the difference between the hypothesis function and the true label times the corresponding input unit, that is x superscript I subscript j. So also, the formula is the same, but we say this is a different algorithm because, this is a logistic regression. Then what's the difference? The hypothesis function is different, right? So your linear function, this hypothesis function is a linear function. So now it is a sigmoid function. So still, this is a different algorithm. Then we studied the multi-class classification. Then what is the solution?
One versus all.
Yeah, one versus all. So for each class, we derive a hypothesis function, right? Then, for example, if we have 3 classes, then we derive 3 hypothesis functions. Then, if I give you a new instance, how would you classify that new instance?
Highest value.
Yeah, so among the 3 hypothesis functions, whichever gives us the highest values, gives us the highest value, then the new instance belongs to that class. So is that clear? Okay. Then in the last class, we also discussed that a logistic regression has no guarantee that
it can do a good job. So if the training examples cannot be linearly separated, we can try, for example, the polynomial regression, but still there is no guarantee that we can separate the positive case from the negative cases. Then in last class, we also discussed the idea of regularization. Then for a regularization, what's the motivation? Why we want to regularize the cost function or overfitting? So very good. So overfitting is also called what?
High variance.
High variance.
High variance, and underfitting is also called high bias, right? Okay. So these are the three cases. So if we continue to use the traditional linear regression for the parameter, then we will end up with a linear line to separate the cases. Then it won't work well. And if we use, for example, the polynomial regression idea, then we can make a curve that separate most of the positive cases from the negative case. So we can do it right. But if we go to an extreme, we add a lot of polynomial terms, then we may end up with a very weird curve that can classify every single training example correctly. But we don't want a case like this. Why?
Given new example, it's going to be a problem.
Exactly. So if we are given a new example, we're likely it won't be able to classify it correctly. So that's the idea of overfitting. So overfitting is more harmful because it sounds very sweet, right? Because your algorithm works pretty well with the training example. We can easily notice underfitting, right?
It's not gonna be able to get through the testing, right?
Yeah, because it makes you look bad, right? So the accuracy is pretty low, so you can easily detect that one. And this one makes you pretty good. For example, in the 100% accuracy. So still overfitting is very harmful. And if the input contains too many features, the learned hypothesis function may fit the training examples very well, but fail to generalize the new examples. This is the idea of overfitting. So we discussed two directions to address the overfitting issue. So do you still remember what are the two directions?
Reduce features.
Reduce number of features
Or weights.
or make weights smaller. So yeah, in order to reduce number of features, we either manually select the features to keep. This won't work very well, and or we use some feature selection algorithm. We'll learn later. Then the second direction is regularization. So the idea is to keep all the features, but we reduce the magnitude of the parameters. The idea is that if overfitting happens, so it may end up with a curve, like this, it works pretty well. But if we reduce the magnitude of the weights, then we may get a curve, like this, something like that. So do you still remember how does the regularization work for linear regressions? Now we are talking about linear regression. Or what is the formula for the cost function? What is the cost function in linear regression? 1/2m and sigma, right? That's the difference of hypothesis function minus y squared. It's something like this, right? Okay. So that is this. Then in order to regularize the weights, then what is the additional item we added to this cost function?
Lambda over 2m.
this lambda over 2m, that's sigma, the square of all the weights. So pay attention. So the weights start from 1. What does that mean? It means that we don't regularize W0 because W0 is associated with the fake feature, right? So pay actual attention. We don't regularize the W0. So suppose we have a hypothesis, a linear function for this, for polynomial regression hypothesis function like this. Then overfitting may happen, something like this. Then we don't regularize W0. Then if we have a smaller value, then very likely we'll have something like this after regularization. So then what will happen if you set lambda to be a very big value?
All weights become very close to 0.
Okay, so all the weights are very close to 0. So W1, W2, for example, for this example, W3 and W4 all are close to 0. Then these terms are cancelled. So basically, HW of x is equal to W0. So then it becomes a constant function. So it won't work. So it doesn't learn anything. So in the future, if you read a paper, if you see L2 regularization, it means this thing. So this is called L2 regularization. So what is L1 regularization? L1 is you remove square, then put absolute value. But L2 regularization is used much more often. Okay, so now for the linear regression, we have the regularized term. So we know that the updating rule for W0 remains the same because we don't regularize W0. So then do you still remember the weight updating rule for Wj? Wj is equal to Wj minus what? Alpha times? Yeah, delta Wj. So then how would you express delta Wj? Huh? Well, then how did you implement your homework assignment? It's going to be sigma, right? Sigma I is equal to 1 to m. Then what? Hypothesis function minus what? Y
Times x of j
times x superscript I, then
of j.
j. So that is this part. So now we have this additional regularization term. Then what is the new updating rule? So we can do this together. So for this term, it becomes lambda over 2m w1 square plus w2 square wn square, right? Okay. Then if we calculate the derivative, for example, with regard to wj, then let me add wj square to this one, right? Okay.
So you just get wj.
Yeah. So if we calculate the derivative with regard to wj, then how about these terms? These are
All
zeros.
constants, yeah.
So then basically it's going to be equal to lambda 2m 2 times what? wj. Then 2 canceled. It becomes lambda wj. Minus m. Minus m.
Oh,
Divided by what? Yeah, divided by m here. Lambda. Okay. So then the new updating rule will be additional term. So that is this
Oh, okay.
1 over m. So this is the original term, right? So this new term is because of the regularization. So if we continue to do the update, so that is wj equal to wj minus alpha times this term. So m over 1. So I just copy it, this term, and minus alpha lambda m times wj, right? Then it's equal to wj 1 minus alpha lambda over m minus alpha, this thing. So in this case, the original updating rule is just wj minus the second term. But now it times 1 minus alpha times lambda over m. So this one is, this one is greater than 0, right? So this one is greater than 0. Alpha, lambda, and m all are positive numbers. So 1 minus this part should be less than 1. Then that's why the weight, the new updating rule makes the weight smaller than the previous updating rule that doesn't use the regularization. So is that clear for this one? Okay. All right. So this is the logistic regression. This is the cost function for logistic regression. Then, if I continue to use the regularization idea, then what is the additional term we should add?
Lambda over
Times W.
The same, right? So that is lambda over 2m, then the summation of the WG square. So this is the same, and also pay attention to j equal to 1. So what does that mean?
W0.
W0 is not regularized. So we don't regularize W0. So we only regularize the regular weights. Okay, so we have already know that W0 is not regularized, right? Then do you still remember the weight updating rule for Wj? Wj is equal to Wj minus alpha times what?
It's the same previous one.
1 over m, then sigma h of xi
Minus
minus y of I times
x.
superscript I, then subscript j, right?
Mhm.
So that is the updating rule. Now, if we add this new term, then what is the new updating rule?
You just
Add the,
add lambda wj over n.
Okay, so that's the same, right? So that is lambda over m times wj. So then the weight updating rule is the same as the linear regression again, right? So in terms of formula, this is the same, but there's still a different algorithm. Why?
The hypothesis function.
Still the hypothesis function is different. Then what is the hypothesis function?
Sigma function.
That's a sigma function. That's 1 over 1 plus e to negative W transpose times x. So then this is called L2 regularization. Okay, so do you have any questions for the regularization? So we'll try to practice this in our third programming assignment. So I will think about it and probably post it on Monday. You can still enjoy the weekend. Okay, so now let's spend a little time on vectorization.
Okay. So for the logistic regression, what is the hypothesis function now? Hypothesis function
Oh,
One
1/2n.
1 over
one plus
Oh, is it just thing?
1
plus
G
negative
negative W transpose.
W transpose times X, right? Okay. So then we also studied the new cost function. So that is E of W is equal to negative. It's hard, right?
Minus
Sigma. I equal to 1n, right? Then it's what? Y squared I log
One
H of super square I plus
One.
1
minus
minus
y
log
one minus
X.
Oh,
Right, so this new cost function, okay. Then the updating rule is the same. So for Wj is equal to Wj minus alpha times sigma I equal to 1 to n and h of x super square I times y times xj super square. Okay. Okay, now let's see how we can vectorize this. So we know that the W transpose is equal to W1. So now we treat W0 equal to B. So we use just Ws plus B. So now let's just talk about W1. So W1, W2, all the way to Wn. Now, how about X? So if times X, W transpose times X, X is X super squared 0, that's from 0. X1, and all the way to, what is this?
X M
M minus 1. So basically, for the weight, this is 1 times n. This is 1 times n. So we have n features, right? Yeah. Then for this input matrix that we have, so this one is n because we have n features n times m. Okay. So this is W transpose times x. Then it is equal to, let's say
Y.
it's equal to z, right? So it's equal to z. That is, if this one times this column, it becomes W transpose times x0, right? Then if this one times the second column, then it's W transpose times x super squared 1. And we go all the way to W transpose times x m minus 1. Right? So then how can we calculate the hypothesis function? So hypothesis function is this, right? So then the hypothesis function h of x actually equal to this one, 1 over 1 plus e to negative W transpose s x0, right? And it just it's equal to 1 over 1 plus e negative W transpose times x. Okay. So, in order to do that, we can use vectorize operation. So it is pretty simple. It is just you use 1 over 1 plus NP dot expose negative z. And then that's it. So then if you use this formula, 1 over 1 plus NP dot exponent negative z, then you will get this one. So this one is what? So this is h of x superscript 0, right? This is h superscript 1. This is h of x superscript m minus 1. So is that clear for this one? Okay. So now if we want to calculate the cost function, so we also need the vector of y. Y equal to what? Y equal to y 0, y1, all the way to y m minus 1. So this is h of x. Okay, so how would you calculate, y superscript I times log h of superscript xi? So this one is easy. For the log, we just use, for example, you can use np dot log h of x. Then each of them becomes this term, right? Then to make it easy, understand it, not just you can call it. So log np dot, for example, log of h of x, h of x equal to what? Equal to log h 0 log h superscript 1 log superscript n. So this is log term, right? Now we also have y. Then in NumPy, there's a element-wise multiplication. So don't use np dot. So np dot is the matrix multiplication. So now we want to perform the element-wise. Then you just use this one, np dot log h of x, just dot y, then it becomes this, right? Then it becomes the term, it becomes log of h superscript 0 times y0, this one times y1, element-wise, this is ym minus 1. Then you want to sum them together, you just use np dot sum the result. Then you get the cost function for this part. So it looks very difficult, but if you calm down and just analyze the outcome, the dimension for each of the operators, then it is not that difficult. So probably now it's too soon to talk to discuss everything about vectorization. So once the programming assignment 3 is released, then you guys, after you start to work on this, then we'll come back to this topic to make it clearer. Okay, so we have spent a long time on this idea because in the future we will study more advanced concepts in artificial neural network, probably also some kind of deep neural network. The overall idea is the same like this.
So that is how you apply the fundamental ideas to solve more advanced problems. So that's why I want to keep the pace slow, and so that you guys can follow. Then in this lecture, we have studied the limitations of linear regression in classification, because linear regression is not bounded. And in binary classification, we want the output to be in the range of 0 and 1. So that brings up the idea of logistic regression. So do you still remember the sigmoid function? 1 over 1 plus e negative t, right? Something like that. Then this is our new hypothesis function, that is 1 plus e negative W transpose times x. So this is new hypothesis function. Then correspondingly, we also have new loss function, right? The new loss function is going to be negative y log h of x minus 1 minus y log 1 minus y. H of x. Okay, then we studied the gradient descent updating rule, right? So it sounds, it looks the same as the linear regression, but since the hypothesis function is different, then it's a different algorithm. Then we studied the multi-class classification. For time being, our solution is
create a hypothesis function for each class.
Yeah, so we develop a hypothesis function for each class, right? Treat one class as positive and the rest as negative. So once a new instance is given, then whichever produces the highest value, then the new instance belongs to that class. Then we started overfitting. So then in order to solve overfitting, we studied the L2 regularization idea. So basically, the term we added to the cost function is the lambda over 2m, then sigma j equal to 1 to wj squared. So this one is m or n. N, because n represents number of features. So this is the L2 regularization. Okay, so do you have any questions for today's discussion? Or do you have any questions for your second programming assignment?
I have a question for when we're applying the sigmoid function for the hypothesis. Is that treated kind of like a scalar?
Can you say it again?
When we were writing out the so when we have 1 over 1 plus e to negative t, well, to the negative w transpose times x, when that's the sigmoid function is being applied, is that treated like a scalar, or is that?
So if we view it like this, right? Then initially we only have W transpose times x. So then the output is, from negative infinite to positive infinite, right? Now if we put a sigma, it becomes 0 and 1. So I'm not sure whether I understand your question. So your question is, we first calculate this, then you put sigma to make it bounded. Then in terms of vectorization, so you use this one to calculate the first matrix. So this now is the matrix, right? So then you use this to calculate the second matrix. So by using np.x whole negative z, for example. Then since you have this term, then the rest is easy. You just put this one np dsp negative z. So now it becomes the new hypothesis function.
So
Thank you.
does that answer your question?
Yes.
Okay.
Good. So any other questions? So later, from next week, eventually we move on to the artificial neural network. So we'll have more than one neurons, and the idea is almost the same as this one, but just we have to deal with a lot of neurons, and also we'll study, the activation function. Now we are discussing sigmoid, but we are not limited to sigmoid. So sigmoid is normally used in the last layer, if you want just have binary classification. Then in the hidden layers, we tend to use something else. So we'll discuss more activation functions in next week. Okay, so today we are done earlier. So enjoy your weekend. Remember that deadline for the submission is tonight. So submit early.
Do you want me to resend that?
Yeah.
I didn't see that. I just read it, but I didn't notice that it's just last name.
Okay, don't worry.